Welcome back, everybody. This is the third and final lecture on Newton's laws. We're going to be talking about Newton's third law today, but I want to back up just a little bit and talk a bit more about weight. So weight is the special type of force that comes about because of gravity, local gravity, if you want to think of it that way, surface gravity, however you want to think of it. And since F equals ma, weight equals m times the acceleration due to gravity, or weight equals mg. And I mentioned last lecture about the distinction we should make between weight and mass. Mass is the amount of stuff that is u compared to a kilogram standard usually, and weight is the gravitational force pulling on you, or the local force pulling on you in the case of the elevator problem. So weight equals m times g. Keep this in mind for a moment. I want to look at the specific case of falling. So this little cartoon, you can see an elephant and a boy falling, and they're falling at the same rate as you would expect. But why is it that they had the same acceleration? If you remember Galileo's explanation, Galileo talked about grapes, identical grapes falling side by side, and then what's the difference between that and grapes falling side by side with a little piece of vine between them? Really no difference at all. Newton has a somewhat more sophisticated explanation for why objects fall with the same acceleration. The reason, is how Newton would put it, would be because the weight to mass ratios are constant. More weight means more force pulling toward the earth. Make no mistake about it. That elephant falling toward the earth is pulled to the earth with a much, much greater force than the boy is going to be pulled to the earth. However, the elephant also has a greater mass, greater inertia, meaning greater resistance to the motion. And those two effects cancel one another out precisely. So g is constant for a given reference frame, which of course is about 9.8 meters per second, or what we've been approximating as 10 if we minimize or assume air resistance is 0. But let's look at this a little bit more sophisticated. So for the elephant, I'm going to use big W for weight. Big W equals big mg, and F equals ma, so big mg equals big ma, and look, the big m's cancel out. You're left with acceleration of the elephant equals g. But for the little boy, it's exactly the same. Little w equals little mg. Or with F equals ma for the little boy, mg equals ma, and the little m's cancel out, and you're still left with a equals g. The weight to mass ratio is the same for both, since both are subject to the same gravitational acceleration, the same gravitational field near the Earth. But this would be true anywhere as long as the air resistance is small. Okay, we're going to move on. When I come back, we're likely going to do a lab to test Newton's second law, where we're going to use cars that are on a track and they're going to be pulled with a weight off to one side. And you can vary the hanging weight and you'll see how the acceleration changes. And you can also vary the weight of the car and see how that changes. It's kind of a fun lab, and that'll be when I return. So let's chat about the third law of motion. You can see it in Latin in case you're interested. You definitely see a couple things there that were probably familiar to you. Actione contrarium. And then you have reactionant. Again, my Latin's pretty bad, but the first translation from Newton is, to every action there is always opposed and equal reaction. Let me say that again. To every action, there is always opposed and equal reaction. Or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. He went on to say, whatever draws or presses another is as much drawn or pressed by that other. If you press a stone with your finger, the finger is also pressed by the stone. So if you're sitting in a chair right now, you're pushing on the chair. But how do you know that? Because you can feel the chair pushing back on your butt and on your back. You literally are pushing down on the chair and you can feel the chair push back on you. That's what you're feeling. When you stand on the ground, what you feel in your feet is the ground pushing back on you. So slightly better way or slightly easier way to remember this is, for every action, there is an equal reaction, or forces always exist in pairs. Some examples. Here's a weird example. In order for you to move forward, to walk forward, you literally have to push backward on the Earth. The Earth actually is what pushes you forward, which is totally strange. Rocket engines propel rockets by pushing hot gases out of one end, and the gases push the rocket forward. The gases come out of the engine with a really high velocity, but the gases have a much lower mass, and they push the much heavier rocket forward with a much lower velocity. Yes, we're going to see that the product of mass and acceleration is the same for both things that are affected during an interaction or during a force exchange. And then finally, if you are familiar with weapons, then you might know that if you fire a rifle or a pistol, there is usually a significant kick back on you, which means there is a proper way to fire a weapon. If it's a rifle, you would anchor it against your shoulder. If it's a pistol, you would likely use two arms. I'm sorry, I don't know anything about weapons other than just basically the physics behind them. Short video for you. You're going to see two students of different mass. Oh, I'm sorry. My apologies. That's coming up. This is the two cars that are going to be pushed apart. Let me get to the. Here we go. So these two cars have the same mass, and I'm going to click on them. There's a spring between them, and watch what happens. Eventually. Okay, you can see there that these two cars of equal mass essentially move apart with the same acceleration. Now let's change up the masses somewhat. I put some little weights on this car on the left. It's really easy to tell that the car on the left is the one that now has a smaller acceleration. Watch, there you go. The one on the right definitely moves way faster than that car. Some other examples, if you were to step off of a boat, or for that matter off of a skateboard, you would move to one side and the skateboard or the boat would move backwards. That would be the reaction. So here, to think about this specifically, the action is the person pushing the boat backwards, which makes the boat move, and then the boat makes the person move forward. If you have two people on skateboards, one pushes on the other, then they both move. Let me show you that. That's real easy to see here. Watch that again. Okay, so it's definitely easy to see that the more massive student is moving with a smaller acceleration than the lighter student is. But the product is the same if we were to work out the math. Sometimes called red car meets blue car, but basically the product of mass and acceleration is going to be the same for both of them, both of the skateboarders, both of the cars here. I'll give you a tricky thought question to think about. Let's say you have two equal weights hanging off of a spring scale. This is like a grocery scale here with a spring inside. And there's a scale on here so you can actually measure the numbers. Let's say you got 100 newtons here and 100 newtons there. What would the scale actually read? So I want you to stop the video and think about this for a minute. What would the scale read? Is it going to read 100? Is it going to read 200? Is it going to read 0? So pause the video for just a moment and then we'll chat about it. Okay, so what do you think is going to happen? Well, it's certainly, you could really make an argument for any one of these cases, 100, 200, or 0. Let's put a couple of these out of the running. 0. It seems like you should read 0. And it's true that there's no motion. However, the scale still has tension in it. So it's not going to read 0. It's like if you push your hands together as hard as you can, you're going to feel, yes, there's no motion on your hands, but you definitely feel pressure in your hands. If you pull your hands apart, you can feel that there's tension in it. So there's clearly going to read there's going to be a reading on the scale. I want you to imagine standing on a scale. You push down on the scale, and it's going to read your weight. The scale pushes back up on you. Now you're probably starting to think of the answer. You might think, well, shouldn't it be 200? Let's take a look. It's actually only 100. Well, why is that? Well, if you replace the weight on the left with just your hand, is there any difference? No, not at all. All your hand will be doing is keeping it in place, which is all that extra weight is doing, is just keeping it in place. So the only weight that's going to be read is just the weight of one side of it, because the other thing is simply holding it in place. Here's another slightly tricky question. Fan on a sailboat. Can it make the boat move? So you might think, well, sure, it's wind that inflates a sail. It's going to make it move. And that is absolutely true. But is there a difference between an external wind and an internal fan source? So think about this for a moment. Will it make the boat move? Well, you're absolutely right to think that external wind should make a sailboat move. That's the whole point of a sailboat. But if you have a fan installed on the boat, It's exerting a force on the boat. Well, specifically on the sail, but on the boat itself. And then the sail pushes back. Aren't they pushing on the same object? The fan can be providing a constant force, but as long as it's directed toward the sail, it's acting like what we might call an internal, not external force. The sail pushes back on it with an equal, oppositely directed force. In order for the fan to move the boat, it has to be directed away from the fan would have to be directed to the left, or it should be simply off of the boat entirely. So sadly, no. If you bring a fan with you on a sailboat, it ain't going to do anything unless you turn it around. You've probably seen swamp boats before that have big fans on one side of them. When you were looking through my notes, I have several examples here that are really worth taking a look at, but I think specifically my favorite one is the one that is done by the Mythbusters people. You really want to take a full look at this video because they use a full size like swamp boat fan right here, and then they aim it at a sail. So that's really worth taking a look at. Something else that's worth taking a look at is a little slide I'm calling real or bogus. So we have a dude here who has a leaf blower and an umbrella. The question is that real? Is it possible? Is it bogus? He basically shows you the setup right here. He's got an umbrella, he's got a leaf blower, and how possible is that? I want you to think about that. And then watch the full video if you can. One other thing to think about before we say goodbye for today, a brain teaser. Let's imagine that you have a sensitive scale and you've got a jar of flies that is basically just you're going to put on the scale. Is the scale reading going to change with the motion of the flies? So the flies are going to be able to fly all around. Let's assume you do this experiment and the flies are going to be alive during it, even though it's sealed up jar. The flies are able to fly all around. Will the scale reading change on this super sensitive scale? This is something I'm going to have you think about in an upcoming lab, and tell me if you think this is going to be, is this going to be a possible change? Whatever you think will happen, this is what I want you to talk about in your lab group. Sorry, I had to take a break there for a second. Yes, so with this super sensitive scale, you're going to have a bunch of flies in it. And I really want you to imagine the fly's weight is enough to make a difference to this super sensitive scale. But is the scale reading going to change as the flies are flying? You could think of this large scale as well. Imagine if you had a drone, like you're flying a drone in a box. A big box that's on scales. Would the reading, and I'm sorry, you have the box and the drone, all of that sitting on like a big scale. Would the scale reading change if the drone is flying? It's a really good problem to think about because it gets at the heart of Newton's third law. So you're going to be thinking about that, and there's actually some video that you can watch. I'm not going to show you what happens here in this video, but if you go to through the rest of my slides on this section, then you will see there's a whole lot of stuff to be gleaned from this. So anyway, you can take a look in the actual notes, and there'll be some links that you can take a look at that are some more Mythbuster stuff that's really, really well done. But I'm going to stop this right now for you to think about, and then when you do the lab tomorrow, there's a question that is pretty much the same question you can chat about with your lab group. All right, thanks, and I will be seeing everybody next week.